here to here. I know this distance. Therefore, I know the velocity. If I know the velocity, I know the kinetic energy. If I know the kinetic energy, I know this. If I know this, I know this, I get kinetic. And that's the reason why this technique is so very powerful. And in fact, this is called time of flight. I'm actually measuring the time of flight of the electron from point A to point B. And how do I do it? I come in with light, the light impinges my gas beam at a certain point. At that time, I start the clock. The electrons are produced. Now they start to move and they reach the detector. A signal is produced that stops the clock. Now, generally, this flight time is in the order of very tens of very microseconds. We keep it that long. And all these timing signals are extremely fast, which means the process of starting the clock and stopping the clock doesn't really act to your time. That's something that you have to wonder. It's like you're trying to measure how quickly a person runs in 100 meters. But then the guy who starts and stops the watch is very slow, then of course you have a problem. Nobody will make it in 9.9. Because this guy will take away 2 seconds just to look at it. So you need somebody who's quick. Of course, they're all electronic stuff. And that's basically what this is. Very quickly it starts it on sub-nanosecond time scale. This one takes a few microseconds. Sub-nanosecond time scale, this will stop the clock, and all you do is go make a readout as to how much time you took. You know the time of flight. You know the distance that can be measured in a variety of ways. And therefore, you know the kinetic energy. You know the kinetic energy, you get ionization potential because you know what the frequency of light is. This is the experimental method, or one of the experimental methods by which photoelectron spectroscopy is done, by which you can get ionization potentials. There are many other methods by which you can measure this kinetic energy. This is just one way, and I explain it to you because it's rather simple. It's like running a 100-meter race. And if you know when you start the gun, that's your start pulse, and the moment you hit the finish line, that's your stop pulse. And your time is measured based on that. And this is exactly what it is. The gun goes off here, stop pulse comes off here, you find it out. So experimentally it's rather simple. Experimentally this is something that is extremely well known today, and all of us know how to do these experiments. You can measure the kinetic energy, you can measure ionization potential accurately. Now let's see whether this information can be used to study the spectroscopy of molecules. One thing is to get ionization potential. That is information you want. But can we go beyond that? Can I use this technique to study the spectroscopy of the system? And let's see how that can be done. Argon. What is the electronic configuration? P6. It's actually S2P6. But in S2P6, what is the term state? Completely filled. Therefore, right? Completely filled. S is filled, P is filled. Therefore, the completely filled shell, I kept telling you, if it's a completely filled shell, there you are dealing with a single S state. No angular momentum, no orbital angular momentum, no spin angular momentum, and therefore it is single S1. What happens to the argon, the ionized state? What's the electronic configuration there? P5. What's the term state for P5? Term state for P5 should be just like the term state for P1. There's only one electron in the p orbital. Then what happens? Pretty simple. You don't have to add anything. Little l equals 1. Therefore, capital L also has to be 1. And therefore, the capital L is 1. What is the term state? P state. There's only one electron. Therefore, what's the spin going to be? Half. Therefore, what is the 2s plus 1 going to be? That's been doublet P state. So, we are looking at a state which is doublet P up there. And we are not done yet. What should the J value? 3 by 2 and 1 1 by 2, and therefore what happens here? I have a 3 by 2 and 1 by 2. It means there will be two states out here. One corresponding to doublet P 3/2 and one corresponding to doublet P 1/2. So when the molecule is ionized and goes from a single S to a doublet P, what will happen? Some of them will get into the doublet P, some of them will get into the doublet P 3/2, and some will get into doublet P 1/2. Which is more stable in this case? 3/2 or 1/2? 3/2, because it's more than half full. 3/2 is more stable, and that is less stable. So which means, who should be the one who will ionize more easily? In other words, look at the energy. Here to here, what is the energy? Here to here, what is the energy? This energy has to be less than this energy. Therefore, from atom jump from here to here, a certain amount of energy is used, that is my energy for H2. Energy used to take this from here to here, and the balance has to go to the electron and kinetic energy. But when I go from here to here, the balance that goes to the electron and kinetic energy is going to be different. That's more we will get, but it's different. So you must get how many bunch of electrons when the process occurs. When I take argon and ionize it, I just kept telling you an electron can be removed and it goes to the detector, you get a start and stop pulse. But in this case, what will happen actually? There will be two sets of electrons, one traveling faster than the other. Because one of these states has a lower energy and therefore will give rise to a faster set of electrons, and another state has a higher energy and therefore will give rise to a slower set of electrons. And therefore, when I do this experiment, what will happen? I will see actually not just one feature, I will actually see two features, one of which corresponds to the dropping of the argon into a doublet P 1/2 state, and the other one is going to be a situation where the argon gets dumped into a doublet 3/2 state. Two states, two P's. So the moment I do the experiment, I see this, and the moment I see two P's, what should I believe in, or what should I immediately conclude? I should immediately conclude I'm probably seeing a doublet state. Because if it's a doublet state, I will get two such P's. So immediately I get to know the spin of the system. So photoelectron spectroscopy, apart from giving me the ionization potentials, it starts telling me quite a bit by the fine structure in the photoelectron spectra. It starts telling me about what sort of a state I am looking at. Supposing this had been, let us say, a single P state. Supposing, let's say some molecule is single P. What will be the J value for that? J value for that has to be, this is N, single P 1. Only one state. But here I have two states. So depending on the spin, you will actually see that the J components can be 2 or 1 or 3 or whatever. And therefore, the fine structure in your spectrum is actually giving me information about the states involved. What sort of states am I really talking about? So in R1, I go from single S. I know the R1 is not changed to single S. And because I see two P's, what should I immediately tell me? That I really gone into a doublet state, and most likely a doublet P state. A doublet P state has two components, a 3/2 component and a 1/2 component. And therefore, they must have different energies for the photoelectrons. One of them will tend to be faster than the other. Why? The one that requires less energy for ionization is going to impart a greater amount of energy to the kinetic energy of the electrons moving out. The one that requires more energy to get kicked out will automatically impart less energy to the electron as it goes streaming out. Therefore, depending on which state you leave it, you actually get two sets of electrons, two packets of electrons, one faster than the other, and you get two beats. And that immediately will start telling as to what the state is. And what is this energy difference going to be? Going to be this. I know somebody asked me, how do I know the energy difference? And I said, I'll tell you later. That later has come today. Because if I know that difference, and that difference is actually the difference between the 3/2 and the 1/2 state, and we call that difference as a spin orbit splitting. Why? Because these states are actually produced because of a coupling of the orbital angular momentum and the spin angular momentum. L and S were coupled, give me J. Therefore, whatever I got over here are actually consequences or results of coupling the L and S, of coupling spin momentum and the orbital angular momentum. And therefore, these are called spin orbit states. And that difference in energy here is called spin orbit splitting. And how do I get information about spin orbit splitting? Anyways, but one of them is telling me right here. All I do is do a photoelectron experiment, and the difference between those two peaks is actually a measure of my spin orbit splitting. I will stop here because I need to rush and get set for the evening lecture. But we'll have an extra class next week, the one I'm still waiting to make out. We'll have it sometime next week.